This is not the easiest unit. It's not necessarily the hardest unit, but doing some of those concentrations and stuff take a little bit of practice. So let me work through my things here, and you can listen to me or not. It is up to you, but I will work through these questions. So starting with number 1, and this, both questions 1 and 2 come from chapter 13. And it starts with a patient weighing 198 pounds was admitted to the hospital diagnosed with pulmonary arterial hypertension. Treprostinil is an analog of and so forth, and it is dosed at 1.25 nanograms per kilogram per minute. So the only tricky part to this question might be the nanograms unit. But I can't trick you, you're smart. So we can deal with that. So it asks what infusion rate in milligrams per hour should be used to treat the patient. Well, I have how much they need. I have a weight here, but I need to get it into ultimately those units. So those are the only trick to that. So let's start with the weight. So if I start with 198 pounds, if I divide that by 2.2, I get kilograms. So good, because if I bring my dose down here and express it as 1.25 nanograms per kilogram per minute, I still highly suggest that you write it like this so that you can see when you cancel one of the units, we are now in nanograms per minute, which means that all we have to do is convert nanograms to milligrams, but minutes to hours. So you can do them in any order you want. Let's start with the nanograms here. And I heard people talking about, is that a million? Is it a billion? What is it? I can never remember, but I do remember it goes from milligram to microgram to nanogram. And each one of those jumps is how much? 1,000. So I work by 1,000. So I did 2 steps. I went first from nanograms to micrograms. And I know that nanograms is smaller, so there's 1,000 nanograms for every 1 microgram. That is the one that's right above nanogram. So that converted me to micrograms. I then remember there's 1,000 micrograms per milligram, so I divide by another 1,000. So at this point, I have converted my nanograms to milligrams. So there's my milligrams. But I can't forget my minutes here. So at this point, I'm going to multiply by 60 minutes per hour. So I multiply by 60 so that minutes cancel and my final units would be in milligrams per hour. And rounding to 3 decimal points gave me 0.007 milligrams per hour. All right? So that's how I got number 1. Number 2, and I think this is walking around as the hardest one, it says if the drug is available, because there's a lot of information, and I give it to you in kind of random order, you have to decide what you need to know first, second, and third. So in this case, I said the drug is available in a 1 milligram per mil concentration. So that's kind of the drug additive, is that. What volume of that additive should I use to make, if I'm going to prepare a 100 milliliter bag? And I'm going to run that bag at 2 milliliters per hour. So I have a total volume, I have an infusion rate, and I have a drug concentration that I'm ultimately going to use. So where do I start? And that's tricky. But in the end, I'm going to need to make enough drug that I have a 100 ml bag. The one thing that's fixed, that's absolute, is the bag I'm going to make is 100 milliliters. So I need to determine the amount of drug for a 100 milliliter bag. So let's start with that. The problem is 100 milliliters doesn't work with what I just answered here, which was 0.07 milligrams per hour. That's per hour. So my first step is to convert my milliliters to hours. So what can I do to do that? I use my infusion rate because my 100 milliliter bag, that's fixed, I'm going to administer 100 mils, is going to be run in or infused at a rate of 2 milliliters per hour. So if I divide 100 by 2 so that milliliters cancel, I can say that that 100 milliliter bag is really a 50-hour bag. And if I had just told you we need to make a 50-hour bag, it would have made more sense because I could just multiply my 50 hours times my 0.007 milligrams per hour, then hours cancel, and I'm in milligrams. That's how much drug I need. But that's in milligrams of drug. So to know how much additive solution I need, I have to know that I'm using a 1 milligram per milliliter additive solution. So then if I multiply it by that, the volume of that solution that provides me the milligrams that I need for a bag that's going to last 50 hours is the 0.35 milliliters. Okay? So I would argue this math is not hard. This is where I strongly suggest and like the dimensional analysis so you can kind of see what you're doing. But it's still hard in terms of where to start. And again, do you see where this is a ratio? That's a ratio. Our answer before is a ratio. What is the only thing that had a single unit? 100 milliliters. So that's, again, look for something like that. That's often where you have to start with. That's the defining amount is a single thing. In this case, it was 100 milliliters. All right. Well, let's move on to number 2. This one I think is a lot more straightforward in the sense it's a straightforward dosing question. I won't read all of it, but it's a 60-year-old patient. But the trick with the dosing here is the dose is based off of body surface area. So this is really going back. That's what I'm saying. This whole course is somewhat cumulative because to determine how much drug you need to infuse, you got to go back and determine their body surface area. So given this information and the formula, I will always provide you the formula. That isn't the issue. We can determine their dose, and given their metered squared, their body surface area, I can determine their dose, and then we can go on and determine the infusion rate. So let's do this a couple of steps at a time. Step 1, just determining their body surface area, the BSA. So I need their weight in kilograms, so 176 divided by 2.2 is 80 kilograms. I needed to take the fact that they were 5 foot 11 inches and convert that to inches, so 5 feet is 60 inches, plus the 11 inches means that their height is a total of 71 inches, times 2.54 centimeters per inch gives me their height in centimeters and their weight in kilograms. Once I have that, it's a plug and chug into the formula, and making sure that I do my square root right and everything else, I ended up with 2, rounding to 2 metered squared. So this patient's BSA is 2 metered squared. Now I have the value I need to base the dose on. Their body surface area is 2 meters squared, so I'll start with that. From the question, it was 50 milligrams per meter squared, so if I multiply that, I get 100 milligrams. Right? Knowing that the concentration of my additive was 1 milligram per mil, then to get 100 milligrams, I need 100 milliliters of the cisplatin, okay? So that's where it gets a little bit tricky. That's the volume of the drug additive that provides 100 milligrams. But I can't just infuse that. It's too concentrated. So it read in the question very clearly that I needed to do what? Add it to 1,000 milliliters of normal saline. So when we add the drug to the saline, then the volumes are additive. So obviously 100 plus 1,000 milliliters gives us a total volume of 1,100 milliliters. 100 is from drug, 1,000 is the bag of saline we're going to inject it into. The total volume is 1,100. Okay, and it said in the question, go back and read it, to add it to 1,000 milliliters. So we know that the drug volumes are going to be additive. So that's my total volume. That's what I have to infuse. I was told that that amount would be infused over 6 hours. But I want the infusion rate essentially in drops per minute. So this needs to be converted to drops and that needs to be converted to minutes. Do that in whatever order you want. This is where we use the calibrations for the set that we're using at 20 drops per mil. If I multiply it by 20, then I'm converted from mils to drops. And to go from hours to minutes, I need to divide by 60 so that in the end I express my drops per minute. And so when I do all that math all the way across, I got 61 drops per minute. Everyone okay with that? So that's chapter 13. Let's move on. This is a good question from chapter 15 where, again, I like this one because there is both a fortification as well as a dilution because we're adding pure sulfur, this amount of pure sulfur, to a cream that is 45 grams of cream that has both two drugs, sodium sulfacetamide and sulfur at that concentration. So would you agree sulfur is going to go up? That's going to go up when we add sulfur, but sodium sulfacetamide is going to go down in concentration because we're diluting it. So don't do both at once. You can do either one first or second. It doesn't matter. I'm going to do the sulfur. I'm going to use the algebraic method, which says C times Q, my concentration times my quantity, plus concentration and quantity, gives me a final concentration and quantity. So let's just list those out. Starting with sulfur, and again, if I listed a sulfur, I'm starting with 4% and 45 grams. That's the cream I have to begin with. And you can see my mass just multiplied over here. What am I adding to that? Pure sulfur powder, and I've emphasized this before. What does pure mean? 100%. So the concentration of that sulfur is 100% sulfur. How much am I adding? I am adding 1.95 grams. what do I get in the end? I don't know what the final concentration is, but my mass is additive. So if I take 45 grams and I add 1.95 grams to it, and that's the only thing I'm adding, then my final quantity would be 46.95 grams. So in the end, when you look at all of these things here, I only have one variable. I only have one x. So if I set this up as CQ, C times Q plus C times Q, equals my final C times Q, then 4 times 45 gives me 180. 100 times 1.95 gives me 195. I add that up, I get 375. 46.95 times x gives me 46.95x. When I divide 375 by that, so I divide by that, I got 8%. And remember, x here represents the concentration of sulfur in my final product. Okay, and it doesn't make sense that if I start with a 4% and I add pure sulfur to it, that the concentration went up. In this case, it went up to 8%. Is everyone okay? That's a fortification. All right, now, what happens with the sodium sulfacetamide? Again, I'm starting at a 10% 45 gram cream. That's what I'm starting with. I'm adding this amount of pure sulfur. So what is the concentration of sodium sulfacetamide in pure sulfur? 0. There's no sodium sulfacetamide in pure sulfur, even though I'm adding 1.95 grams of it, and I'm still solving for the final concentration. But again, my masses, even though there's no drug in that 1.95 grams, there's still mass in that drug. So again, my final mass will still be 46.95. In the end, since there is no drug concentration of sodium sulfacetamide in the sulfur, there's no mass of sodium sulfacetamide, so really M1 is simply just equal to M3. All right, so the 10% times the 45 grams is going to equal my final product, which is some X concentration times the total weight, which is the 46.95. Do a quick math, 450 divided by 46.95 means that its concentration will go from 10 down to 9.6%. So this is the final concentration. That makes sense? So C's and Q's and kind of remembers those. And this one question had both a fortification and a dilution all in one. All right. Now, question 4 is I'm going to solve this using the alligation. And I will still remind you on the test, since I don't check your work, you can solve this however you want. If you want to do it through algebra or you do it through alligation, you could have done the previous questions using alligation as well. So it is totally up to you. I would tell you, I'd like you to become skilled at both, but in the end on the test, do the one that works for you. If there's one way that you like to solve these, do it. I don't care as long as you get the right answer. So in this question, we're going to start with a 17% gel. How much of that do we combine with 40 grams of a 3% gel so that we end up with a higher strength of 6%? So here is my high. That's supposed to be an H. I know it doesn't look like that. Here is my low, and this is my middle. This is what I want. All right? So in the alligation method, what we do is we start with our high on top. So there's the high strength there. We put our low strength right below it. And remember, our target, our desired, is in the middle to the right. All right? So does everyone see where the 17 and the 3 and the 6 comes from? Those are our concentrations. The high concentration ingredient above the low concentration ingredient. And to the right and to the middle is our target, our desired concentrations. And then we have these cross arrows going diagonally down and diagonally up. What do we do? What's at the end of those arrows? We subtract. Remember, just subtract. Always the highest from the lowest. So don't ever get a negative number, just subtract. So what going down, what is 17 minus 6? 11. Okay? Going up, what is 6 minus 3? 3. These are now parts. You notice it doesn't say anything about a percent there. And the trick to remember, this arrow going this direction reminds you that the 17% has 3 parts and the 3% has 11 parts. And to be honest with you, just as a reminder, if you wanted to know the number of parts of your final mixture, it's these added together. So 3 plus 11 is 14. So there is 14 parts of the 6%. So do you see where I have concentrations and parts? And remember, to go on further, all we need to do is put our P's over our Q's, our parts over our quantity. I would argue we only know one quantity. There's only one quantity we know. We know 40 grams. 40 grams of what? 3%. Which parts was 3%? 3% had 11 parts. So that's where that comes from. I'm going to put my 11 parts over my 40 grams. I know 1 P over Q. I know that the 11 parts of the 3% has 40 grams. And I know the P's and the Q's for every other ingredient are equal to that. So P over Q equals P over Q equals P over Q. So here are all of my parts that I just solved for. Here's the parts of my 17%, which I'm really solving for, over X. I don't know its quantity, but I know its parts. And if I know this is equal to each other, I can solve for that. 3 over X is equal to 11 over 40. That's all I'm having to do. So 3 times 40, 120, divided by 11, solves for 10.9. And that's 10.9 would be the grams of the 17% gel that I need to add to my 3% gel to get my final mixture. Okay? So do you see where there's not a lot of math involved, but this is a very visual thing. You do need to be able to set it up correctly, cross-subtract, put the right parts with the right quantity, and solve for what you want. But it is a visual way of doing it without having to do all the C's and the Q's and the C's and the Q's, and less algebra, if you will. Okay, so the final answer here would have been the 10.9. Are we happy? You don't look happy, but we will move on. All right, so either way, make sure you can do an allegation or do a CQ type thing. All right, this goes to chapter 22, and I've mixed in this one question both not 22, I'm sorry, both the 16 and 20. If you remember, 16 was easy. It's recipes. How do you adjust your formula, your recipe, either up or down if the amount you want to prepare isn't the same that's called for in the prescription? Because here in this prescription, we have all of these parts added up, and it doesn't even give us a total amount, all right? So in this case, though, we want to prepare 40 bottles of that mixture, each containing 1 ounce. So in the end, I'm going to ask you, how much of each ingredient do I need? So remember, step 1 is to determine the desired amount. How much are you wanting to prepare? I want to prepare 40 bottles at 1 ounce, and that each ounce is 28.35. So would you agree, when I do that math across, what I want, what I desire is 1,134 grams of the total mixture. I don't know of the individual amounts, but I know the total of the formula. I want total mixture of 1,134 grams. All right? Then simply add up the weights of all the ingredients. What's tricky here is I don't know the weights, but I don't care. Add them up. I know parts. So I know 2 parts, and if all of my ingredients are mixed together, 2 plus 8 plus 2 plus 1 plus 1, add that all up, and of my formula, if I add everything, I have a total of 14 parts. So 14 parts are called for in the formula. This is the biggest thing here, and I will give you this adjustment factor formula if you need it, but you still have to be able to understand how to interpret this. It's the total amount to prepare, so the amount that I want to prepare is 1,134 grams over the total amount in the formula, which I said was 14 parts. Now, grams and parts do not cancel out each other, okay? So I don't get a unitless multiplication factor, but I do get a multiplication factor, in this case, when you divide that out, of 81 grams per what, though? Per part. I need 81 grams per part. Per part of what? I don't care. Per part of anything. For every part of any ingredient, I need 81 grams per part. So simply then, to determine the amount of each ingredient, take the number of parts that called for in the formula times the same factor that we just determined. We needed 81 grams per part. Multiply it by every one of those parts, and you get each individual amount in grams. Okay? Now this is one example, and the other examples in that unit, they did divide out. Instead of giving it to you in parts, I gave you a weight, but you add up the total weight, and you get just a multiplication factor. In the end, the multiplication factor is just multiplied by whatever amount is called for in the prescription. All right, now before we go on, I want to just point out this number here, 162 for zinc stearate and 81 grams for magnesium stearate, because the next question is, all right, these are out of stock. I don't have zinc stearate and I don't have magnesium stearate, but I need them as my source of zinc and magnesium. So what I'm going to do is I'm going to use zinc oxide instead of zinc stearate, and I'm going to use magnesium carbonate instead of magnesium stearate. So far so good. Different salts of zinc and magnesium, but I now need to figure out how much of that salt will give me the same amount of zinc or magnesium. So starting with the zinc, so what I need to do is let's set up and figure out. There's 2 ways of doing it. There's step 1 and there's step 2, okay? And so I'm running out of time, so I'll do the easy way here. So would you agree here we have a molecular weight of the 2 ingredients? So let's just set those up. The zinc stearate is here. The molecular weight of the zinc oxide is there. So again, the amount that I needed from the previous question was 162 of the stearate. You set that over X, and do you see where stearate over oxide equals stearate over oxide? X equals the amount of oxide that I need. And you can solve for that and go directly to that amount. You can see the same exact work here for the magnesium. We have the amount of stearate molecular weight, the magnesium carbonate's molecular weight on the bottom. I knew I needed 81 milligrams of the stearate, not milligrams, grams, and solved over X, and I got that. Okay? These were pretty straightforward, so I'm trying to get through this as quick as I can so we can get to, these are both really good realistics. And I will tell you now, part 2 of this is an endless practice problem. So if I don't get much time on that, it is an endless practice problem. So make sure you prepare and know how to do that. So here's again for acetaminophen, and I'll just read the question. What is the amount of unbound drug in the blood, basically, based on the bioavailability and the protein binding? So these are the two things we need for this question, to know how much of this acetaminophen gets into the blood. We're going to start with 2 500 milligram tablets. 2 times 500 is 1,000. And if its bioavailability is 88%, that means 88 milligrams will be absorbed for every 100 milligrams administered. So that's how much gets into the blood. But not all of that is free. It's 20% protein bound. But notice here, this is the trick. If you guys are listening to me, don't multiply by 20%. I want to know how much is unbound. So if 20% is bound, how much is unbound? 80%. So what I'm multiplying by here is 80%. I want 80% of 880 milligrams, and that's the final answer there. So 704 milligrams represents 80% of the amount absorbed, which is 880 out of the 1,000 administered. Okay? So this is the other thing that we practiced, was using that formula, and I'll give you that formula here. The dose is equal to the volume of distribution times the plasma concentration. In this question, though, the problem of the volume of distribution is in liters per kilogram. So I have to take the patient's weight first, convert it to kilograms, then I can multiply it by the volume of distribution to get a patient-specific volume of distribution. So this patient's VD for that formula is 45 liters. So if I put that here, I got my plasma concentration, which was given right here, but the problem here is that concentration is in milliliters. So liters times 1,000 gives me that same value in milliliters. You multiply by the 2, and I'm good, except for this is in micrograms, and I wanted it in milligrams, so if you divide by 1,000, that gives me my dose there.